The F1TENTH competition is a platform for graduates from around the world to create and compete using cutting-edge autonomous driving algorithms that push the limits of 1/10th RC scale cars. The aim of our final year project is to participate in the 21st edition of this competition held in Abu Dhabi at the IROS 2024 conference with our car Chronos and a unique software algorithm for winning the competition.
Mimicking races, the F1TENTH competition includes inspection, time trials, and head-to-head races. For time trials, the goal is to achieve the fastest lap or most lap within 2 to 5 minutes heats on a known track. In the head-to-head races, two cars race simultaneously on a simpler track, with the format being determined by the number of participants, which allows overtaking on both sides. Although maps are unknown prior to race day, teams are provided a designated time slot to map the track.
Our build process starts with the RP LiDAR, a high-frequency 2D LiDAR that accurately measures the distance to obstacles, feeding the data to our main processor, the Jetson Nano. This compact yet robust unit processes the information, and through the REST-6 Edu motor controller, it executes precise driving commands to ensure safe and swift navigation. Operations and diagnostics are monitored remotely via SSH from a client laptop using Foxglove. To boost safety and reliability, we integrated the F1TENTH recommended power board for effective power management and component protection. Additionally, our vehicle features telemetry control by a PS4 controller with a deadman switch, enhancing operational safety under human supervision. The car employs 4-wheel drive, giving us more traction and accommodating steering, allowing differential wheel turning for optimized track handling. Due to budget constraints, we opted against the suggested high-end components like the Jetson Orion NX and Herculeo LiDAR. Instead, we chose cost-effective yet reliable alternatives like the Jetson Nano and RP LiDAR A2, achieving the same competitive performance without overspending.
Over the past year, our software development has centered around the F1TENTH Gym Raw simulation environment. This powerful tool allows us to rigorously test and redefine our algorithms in a controlled, repeatable settings before deploying them in a real world. In our exploration of software strategies, we focused on 3 key approaches to determine the most effective one for our needs. The first one is reactive algorithms. So these algorithms enable Chronos to dynamically interact with the environment, effectively navigating obstacles and quickly responding to sudden changes on the track. The second one being conventional autonomous stack, which we explored traditional autonomous driving techniques, which includes precise path planning and optimized navigation algorithms tailored for the intense demand of high-speed racing. And finally, the third one being the learning algorithm, which we also experimented with integrating machine learning to enhance the adaptability and intelligence of our vehicle. By training models within the simulated environment, Chronos continuously refines its decision-making skills. So, utilizing the F1TENTH gym for both development and testing has allowed us to rigorously evaluate these models, ensuring that our software approach is not only innovative but also effective for our hardware capabilities. LiDAR scans the environment, detecting and identifying objects and boundaries. During the mapping round, using SLAM or simultaneous localization and mapping, we create and continuously update a map of the environment while accurately tracking the vehicle's location within it. With this map, our global planner devises the overall race lap strategy, while a local planner handles immediate maneuvers such as overtaking. Based on the control systems precisely executes driving commands, adjusting steering, acceleration, and braking to navigate the track effectively.
Reactive enable vehicles to make quick decisions based on immediate sensor data without relying on maps. These strategies allows car to dynamically respond to obstacles and environmental grid changes crucial for high-speed navigation. Wall following involves using a PID controller to maintain a constant distance to a wall, allowing a car to drive autonomously by continuously adjusting its steering based on LiDAR sensor data. The method calculates the error between the desired and the actual distance from the wall. Using this error to determine the steering angle required to correct the car's path, this approach is particularly useful in controlled environments like racetracks. The gap Strategy is used to navigate through openings between obstacles and identifying gaps within the sensor's field of view. This method involves scanning the environment with LiDAR, setting a safety bubble around the detective obstacles, and identifying the largest available gap free of obstructions. The car then steers towards this gap, dynamically adjusting its trajectory in real time to avoid collisions while optimizing its path toward the rest clear area, thus maintaining high speeds and efficient maneuvering in clustered areas. However, the limitations of these methods are such that wall follow may restrict optimal racing lines and aggressive overtaking by sticking closely to the wall, while gap follow can compromise lap times by focusing on gap navigation over speed and racing lines, with oversteering potentially causing the car to drive backwards.
A racer optimizes a vehicle's path around the track to minimize lap times by strategically navigating turns and maximizing speed. It is generated by parameterizing the path as a spline, a piecewise polynomial that provides a flexible yet accurate representation of the path. The shape of the race line is manipulated by adjusting the spline parameters. This plan is then optimized with convex optimization techniques to ensure it adheres to the physical and performance constraints of the vehicle, such as maximum speed and steering limits determined by the curvature at various points along the path. By integrating splines with velocity profiles, we can define the path as desired target coordinates and speed at different segments, optimizing for the fastest possible lap time. Having established an optimized race line, we can then implement a control to follow the planned trajectory using actionable driving commands. The Pure Pursuit Controller is a path tracking algorithm that works by calculating the geometry between the vehicle's current position and a look-ahead point on the desired path. It calculates the look-ahead distance LD dynamically based on the vehicle speed V and a factor K reflecting the path conditions. This method is particularly effective in racing scenarios where precise and agile maneuvering is critical for optimal performance.
The motor predicted control (MPC) at each time step starts by determining the current state of the vehicle. It then computes the sequence of control inputs that minimizes a predefined cost function over a future horizon, taking into account model predictions and actuator constraints. The model used in MPC typically linearizes the vehicle dynamics. The constraints ensure that the states and inputs remain within feasible limits. The cost function in MPC is usually quadratic, emphasizing both the state error and control effort. Here, Q and R matrix penalize deviation from the reference path and control effort, respectively. The MPC applies the first control in the sequence, then recalculates based on the updated state in a receding horizon manner. This allows for a continuous adaptation to the changes in the vehicle environment and dynamics, ensuring an optimal performance.
Significant advantages in autonomous racing, particularly in handling dynamic and unpredictable environments. Traditional methods such as SLAM can struggle with rapid changes in map, such as the ones that are caused during collision of cars in the track during competition. By leveraging deep learning, we can continuously refine our vehicle's understanding and interaction with the track, maintaining optimal performance despite disruptions. A supervised learning approach for teaching a car how to drive. Data is first pre-processed, where it's downsampled from 1017 LiDAR inputs to 128. The steering and speed are then normalized, followed by time-step synchronization. Given that the motor controller pulls data faster than LiDAR, we use a 1D interpolation method to get the nearest neighbor approximation for speed and steering during a certain scan. Since Pure Pursuit with a race line provides the best performance, this is used as the ground truth for training the model. The agent is a multi-layer perceptron with 2 hidden layers. This processes 128 inputs and predicts 2 outputs, which will be the steering and speed. Now, training occurs in batches, where the agent learns how to replicate the expert driving outputs, optimizing a weighted loss function that prioritizes accurate steering predictions. Our model initially showed inconsistencies at higher speeds, and sometimes even at lower speeds hit the track bounds. To address this issue, we implemented Dagger, or dataset aggregation. If a vehicle comes too close to an obstacle due to accumulated error in predictions, the gap follow node that we previously mentioned activates to correct the course. The collected data is then fed back to the training loop, and the model is continuously improved. Ultimately, based off the results, we can see that we've built a model that successfully avoids collision and is able to adapt to a dynamic track condition. However, it does deviate from the race line in certain scenarios and is very slow. This adaptability is crucial for real-world applications where conditions are unpredictable and constantly changing. In conclusion, we have proposed a simple and adaptable strategy that does not require any complex dynamics modeling. Through meticulous data capture and analysis, we have refined our algorithms and enhanced our vehicle performance across diverse conditions. As we look ahead, we are excited to focus on the following improvements. We will integrate mapping techniques and dynamic race optimization, allowing us to adeptly navigate evolving track conditions during race state. We will also implement an auxiliary loss function in our training loop to smooth out consecutive predictions of our model. We intend to explore different model architectures such as recurrent neural networks to handle time series data, boosting our vehicle's predictive capabilities. These strategic initiatives will propel us towards our goal of developing a fully autonomous vehicle while preparing us for a standout performance at the upcoming IROS Dubai 2024. Thank you for your attention. We are committed to pushing the boundaries of autonomous vehicle technology and are eagerly waiting to showcase our progress in Dubai.